Download this code from codegive.com, link in the description below. OK, let's delve into the, admittedly morbid but technically interesting, topic of simulating beach town obliteration using code. We'll focus on a hypothetical coastal town and simulate the impact of a catastrophic event, like a tsunami or a major hurricane surge. Please remember that this is a theoretical exercise for educational purposes only. Real-world disasters are devastating, and this simulation should not be interpreted as trivializing them. We will be using Python with libraries such as numpy, matplotlib, and potentially scipy for scientific calculations. Setting the stage, defining the coastal town. First, we need to represent our beach town. We'll simplify it for the simulation. Think of it as a rectangular grid where each cell represents a block or area. We'll assign attributes to each cell like elevation, building density, and population density. Explanation **. 1 Coastal town class **. Asterisk underscore underscore init underscore underscore, self, width, length, cell underscore size, initializes the town's dimensions, in grid cells and meters, and creates a numpy array, self.grid, to hold cell objects. Using type equals object allows us to store custom Python objects in the grid. Asterisk initialize underscore terrain, self, beach underscore slope, inland underscore elevation, sets the elevation for each cell, creating a sloping beach. It uses a simple linear model but can be extended to incorporate more realistic elevation data, example from a digital elevation model. We added dunes as well. Asterisk initialize underscore population, self, coastal underscore density, inland underscore density, assigns population densities, making the coastal areas more densely populated. It uses an exponential decay model to simulate the decrease in population density as you move inland. It converts densities to people per square meter. Asterisk initialize underscore building underscore density, self, coastal underscore density, inland underscore density, similar to population density. This sets the building density, which represents the fraction of a cell occupied by buildings. Asterisk plot underscore attribute, self, attribute, title, creates a heat map visualization of a given attribute, elevation, population density, or building density, using matplotlib. This is crucial for visualizing the town's layout and understanding the initial conditions. The dynamic attribute access getAttr, self.gridIJ, attribute, lets us plot any attribute defined within the cell class. Asterisk get underscore total underscore population, self, calculates and returns the total population of the town by summing the population density of each cell and multiplying by the cell area. 2 cell class asterisk. Asterisk underscore underscore init underscore underscore, self, elevation, building underscore density, population underscore density, a simple class to hold the attributes of each grid cell. This makes it easier to organize and manage the data. We added water underscore depth and debris. 2. Simulating the catastrophe, the flood, tsunami or hurricane surge. Now, let's simulate the inundation of the town. We'll use a simplified model to calculate the water depth at each cell. A more sophisticated model would involve fluid dynamics simulations, but for this exercise, we'll assume a static water level or a simplified surge model. Explanation asterisk. 1 simulate underscore flood, self, water underscore level, asterisk. Asterisk iterates through each cell in the grid. Asterisk calculates the water underscore depth for each cell as the difference between the water underscore level and the cell's elevation. If the elevation is higher than the water level, the depth is 0. Asterisk tracks the number of flooded cells, the total population affected, based on the population density of flooded cells, and the estimated building damage. Asterisk prints summary statistics about the flooding. 2 plot _ flood _ depth, self, asterisk. Asterisk creates a heat map visualization of the water depth across the town using matplotlib. The map equals blues argument makes the flooded areas clearly visible. 3. Adding complexity, debris and building damage. Let's make the simulation a bit more realistic by considering debris accumulation and how it affects the town. We'll introduce a simplified model where building density affects debris generation, and debris affects the impact of the flood. Explanation asterisk. 1. Calculate _ debris, self, debris _ factor equals 0.5, asterisk. Asterisk estimates the amount of debris in each cell based on the building density and water depth. The higher the building density and water depth, the more debris is generated. The debris _ factor controls the overall amount of debris produced. Asterisk cell.debris equals min, cell.debris, 2.0, this caps the debris level to a maximum value, 2.0, to prevent unrealistically high debris accumulation. This is important for model stability. 2. Simulate _ damage, self, velocity _ factor equals 0.1, debris _ impact _ factor equals 0.2, asterisk. Asterisk calculates building damage based on the debris, water level, and building density in the area. Asterisk has a cap on the damage at damage equals min, damage, 1.0. 3. Plot _ debris, self, asterisk. Asterisk visualizes the debris accumulation across the town using a heat map with the YL or BR color map. 4. Extensions and improvements ****. This simulation is a simplified model. Here are some ways to make it more realistic. More realistic terrain ** use real-world elevation data, example from a digital elevation model, instead of a simple linear slope. Fluid dynamics * implement a basic fluid dynamics simulation, example using the shallow water equations, to model the flow of water during the event. Libraries like scipy.integrate could be helpful for this. Building strength * introduce a building strength attribute to each cell. Stronger buildings, example reinforced concrete, would be more resistant to damage. Evacuation * add a model for evacuation. Consider factors like warning time, road network, and evacuation routes. Economic impact * estimate the economic impact of the disaster based on the damage to buildings and infrastructure. Interactive visualization * use libraries like Plotly or Bokeh to create interactive visualizations that allow users to explore the simulation results in more detail. Hazard maps * generate hazard maps that show the areas most vulnerable to flooding based on different water levels and event scenarios. GIS integration * integrate the simulation with GIS, Geographic Information System, software to use real-world data and visualize the results in a geographic context. Example of using scipy to simulate water flow, shallow water equations, conceptual. This is a very basic example of how you might start incorporating the shallow water equations. It's significantly more complex and requires a good understanding of numerical methods. Important notes about the shallow water equations example ***. Simplifications ** This is a highly simplified 1D implementation of the shallow water equations. Real-world tsunamis and surges are 2D or 3D phenomena. Numerical stability * The shallow water equations are notoriously difficult to solve numerically. The choice of numerical scheme, example Runge-Kutta fourth order, time step, dt, and spatial step, dx, is crucial for stability. You may need to experiment with these parameters to avoid oscillations or divergence. Asterisk boundary conditions. Asterisk the boundary conditions are very important. The example uses a simplified fixed water height boundary. More realistic boundary conditions might involve inflow/outflow conditions or sponge layers to absorb waves. Asterisk momentum equation. Asterisk the momentum equation is very simplified here, no advection term or friction. A complete implementation would require considering these terms, which adds significant complexity. Asterisk computational cost. Asterisk even a simplified shallow water simulation can be computationally expensive, especially for large grids and long simulation times. This tutorial provides a starting point for simulating coastal town obliteration. Remember to use this knowledge responsibly and ethically, and to focus on understanding the science behind these events and promoting preparedness and mitigation efforts. Always keep in mind the real-world impact of disasters and avoid creating simulations that could be misinterpreted or used to cause harm.